Hello, my name is Govind Santosh Pathak, and this is my final project for the course CS6271, which is Evolutionary Algorithms and Humanoid Robotics. The project is titled as Predicting Income Using Genetic Programming. It was supervised by our module leader, Professor Connor Ryan at the University of Limerick, and I am submitting it as a part of the Evolutionary Algorithm final project. Income inequality is a persistent socio-economic issue, and predictive models can help identify patterns that support decision making. Traditional machine learning approaches often achieve strong accuracy, but they operate as a black box model with limited interpretability. In contrast, our genetic programming evolves symbolic expressions that are transparent and human readable. This project applies GP, which is genetic programming, to income prediction, aiming to balance accuracy with interpretability and to demonstrate its potential as an alternative to conventional machine learning methods. The dataset used in this project is the modified version of adult income dataset provided by the module leader. It contains 39,073 entries along with the 15 feature columns with both categorical and numerical features. Categorical features include attributes such as work class, education, marital status, occupation, relationship, race, sex, and native countries. Various numerical features include age, FNLWAT, which is final weight. In other words, this is the number of people the census believes the entry represents. Education level as a number, capital gain, capital loss, and hours worked per week. The target variable is the binary, which is predicting whether an individual's income is less than or equal to $50,000 or greater than $50,000. This dataset provides a balanced mix of demographic and employment information, making it suitable for evaluating our genetic programming in the classification tasks. To prepare the dataset for genetic programming, several pre-processing steps were applied. We began with the raw dataset. Categorical features were transformed into binary indicator columns using one-hot encoding to make them suitable for the numerical computation. Next, numerical features were standardized using z-score normalization. The dataset was then split into training and validation set with an 80 by 20 ratio, and a fixed random seed was also applied for a consistent reproducibility. Finally, evaluation was carried out using the F1 score, which balances the precision and recall. This pipeline ensured that the data was clean, consistent, and ready for the GP evaluation. Let's explore the genetic programming setup used in the project. The project is implemented with the deep library in Python. The function set includes arithmetic operators such as addition, subtraction, multiplication, and protected division, along with the non-linear functions like sine, cosine, exponential, logarithm, hyperbolic 10, and square root. Additional functions also includes negation, absolute value, clipping, and min-max operations. Ephemeral constants are randomly generated values in the range from -2 to +2, which allows the flexible numeric tuning during the evolution. The GP run was configured with a population size of 150 and a 60 generation, with a crossover probability of 0.9, mutation probability of 0.02, and a maximum tree depth of 12, and also the tournament selection size of 5. These parameters were selected to balance exploration, convergence, and interpretability in the evolved symbolic expressions. For this project, the evolution process was aligned with the Kaggle's competition framework. Kaggle uses accuracy as the primary metric to rank submissions. The test set is split into two halves. The public leaderboard is based on the first per 50%, which is visible during the competition, while the private leaderboard uses the remaining 50% and is revealed only at the end. This setup encourages generalizable solutions rather than the leaderboard overfitting. The best individual evolved through my genetic programming achieved a Kaggle public accuracy of 76.66%, demonstrating strong generalizations and competitive performance. For this project, the key evolution was carried out through Kaggle's leaderboard system. After generating the submission file using genetic programming, the model was scored on Kaggle's public leaderboard, which uses half of the test set. The best individual achieved a public accuracy of 77.66%, placing competitively among other submissions. This result demonstrates that the evolved symbolic model was able to generalize effectively beyond the training data. Here on the left hand side, we can see the symbolic expression for the best individual, and on the right hand side, we see the genetic programming tree structure for the best individual. This tree represents the symbolic expression evolved to predict income. Each node corresponds to an operator or function such as arithmetic or non-linear transformations, while the leaves represent input features or constants. The tree highlights the interpretability advantage of genetic programming, showing exactly how features are combined to produce predictions. This transparency is a major strength compared to the black box models. In conclusion, this project applied genetic programming to income prediction using the adult dataset. The approach focused on evolving symbolic models that are both interpretable and competitive. The best individual achieved a Kaggle public accuracy of 77.66%, confirming the effectiveness of symbolic evolution in this context. The key contribution is demonstrating that genetic programming can balance accuracy with transparency, offering a viable alternative to black box classifiers. Future works could explore hybrid approaches, deeper parameter tuning, and extended feature analysis to further enhance performances.